Welcome to today's lecture on the Diffie Hellman algorithm. This algorithm is a cornerstone of modern cryptography and is widely used for secure key exchange. It allows two parties to establish a secret shared key over an insecure public channel. This key can then be used for encrypting communication. In this session, we will break down its steps, components, and applications. This diagram demonstrates the Diffie-Hellman key exchange algorithm step by step using an example with two parties, represented by an Alice and Bob. So, both Alice and Bob both will agree on two public values. So, P is equal to 13 we are taking, which is a prime number modulus. And G is equal to generator modulo P, which is 6. These values are publicly known and is used in the calculations. Each party generates a private key. Ali's private key is 55 and Bob's private key is 44, which is kept secret. Using the formula of public key, G of G power private mod P, Alice calculates her public key 6 power 5 mod 30. So 6 power 5 is 7776 mod 30. So the public key value we are getting is 2. So this is Ali's public. So Bob's calculates his public key. The formula we are using G power private mod P. So 6 power 4 mod 13. 6 power 4 is 1296 mod 13, which is equal to 9. So the public key of Bob's is 9. The public key of Bob's is 9. Then both parties exchange their public keys. Alice sent her public key 2 to Bob and Bob sent his public key to Alice, which is 13. Sorry, which is 9. So each party uses their private keys and the received public key to calculate the shared secret key. Alice computes public power private mod P. So we are taking here 9 power 5 mod 13. The shared secret key we are getting 3 and Bob computes 2 power 4 mod 30. 2 power 4 is 16. 16 mod 30, which is equal to 3. So both arrive at the same shared secret. The same shared secret key value is 3. The shared secret 3 is now known to both Alice and Bob, but remains unknown to any eavesdroppers, ensuring a secure key exchange. So these are the key insights in the Diffie Hellman key exchange algorithm. The public parameters P and G and public keys A and B can be transmitted over an insecure channel. Private keys A and B are never shared, ensuring the security of the shared secret. This shared secret can now be used as a symmetric key for encryption and other secure communication methods. We are using Diffie Hellman algorithm relies on three key components. Public parameter selection. First, both parties agree on two values, a large prime number P which acts as the modulus, a primitive root G which serves as the generator modulo P. Private key. Each party selects a private key that is kept secret. For example, party A chooses A and party B chooses B. Public keys. These private keys, each party computes their public keys. Party A calculates A is equal to G power A mod P and party B computes B is equal to G power P mod B. These public keys are then exchanged. Let's go. The shared secret key calculation. Now each party uses received the public key and their own private keys to calculate the shared secret. For a party A, x is equal to p power a mod s is equal to b power a mod b we are taking. For party B, x is equal to a power b mod b we are taking. So the shared secret s is same for both the parties, given by s is equal to a g power ab mod t. This shared secret can now be used as cryptographic key. The Diffie-Hellman algorithm is secure because of the discrete logarithm problem. This problem involves finding x in the equation g power x mod p, which is computationally infeasible for large values of p. Even if an attacker knows g, p, a, and b, these are the values, they cannot derive the shared secret s without the private keys a or b. This ensures the confidentiality of the key exchange. Let's discuss about the advantages and disadvantages of Diffie-Hellman key exchange algorithm. It provides a secure way to exchange keys even over an insecure channel like the internet. It eliminates the need for prior key distribution, making it very practical for real-world applications like secure online communication. Coming to the disadvantages, this algorithm is vulnerable to man-in-the-middle attacks if authentication is not implemented. Diffie-Hellman on its own does not provide encryption or authentication. It only facilitates the secure exchange of keys. This means additional measures are required to ensure security. Finally, let's look at where this algorithm is applied. This algorithm is applied or used in secure communication protocols like HTTPS for secure browsing and VPN for private internet access. You will also find these in technologies like TLS, SSH, and IP security, where security exchange is a critical component. So, with this, we have concluded our session. But let's go to the coding part of this Diffie-Hellman key exchange algorithm. So this is the step-by-step explanation of the C program implementing the Diffie-Hellman key exchange algorithm. We are using the header files, which include standard input-output functions like printf and scanf, math.h, which provides mathematical functions. Coming to the modular function, so this function calculates base power exponentiation by squaring method. So we ensure base is equal to base percentile mod ensures the base is within the range of the modulus. And if exponentiation mod 2 is equal to 1 means it multiplies results by base. Exponentiation is equal to exponentiation forward 1. It shifts exponentiation to the right dividing by 2. Then this base square modulo mod is computed for efficiency. This avoids computing large powers directly and reduces the computational complexity. So this is the function to compute base power exponentiation percentile mod. Coming to the input parameters we are taking here. So this is our main function. So we are defining the primary key, prime number and primitive root, private keys and public keys and shared secrets also we are taking in the form of here. So first we are taking key as a prime number which is used to generate keys. G, a primitive root modulo B which is used to generate keys. These are the public parameters shared in between both the parties. This is the alias private key A and this is the box private key B. These values are kept secret and are not shared. Then we will calculate the public keys using the private keys A comma B and public parameters T comma G. So the program calculates the public keys. Alias public key is A is equal to G power A mod B and these public key is G power B mod B. These public keys are shared with both the parties. Then Finally, we will display the keys here. So Alice public key A. This program displays the calculated public keys A and B. Then we will compute the shared secrets in this function in this program using a private key and other parties public key. Both Alice and Bob compute the shared secret key. Alice computes S is equal to B power A mod B and Bob calculates S is equal to A power B mod B. Both calculation results in the same shared secret key S thanks to the mathematical properties of the Diffie Hellman algorithm. And the program displays the shared secret key as computed by each party. So the key exchange was successful and both parties can use S, which is a shared symmetric key. If the secrets do not match, an error is displayed. This should not happen unless there is a bug or interference. Both parties independently arrive at the same shared secret S, even though they only exchange their public keys A and B. The shared secret key S is never transmitted, making the protocol secure. So with this, we will conclude the session showing the program output. So here we are taking the values of prime numbers. The prime number values we are taking here. P value is 13 and G value is, which is a primitive root, 6. And Li's private key is 55 and Bob's private key is 44. Then the Li's public key we are calculating with the help of P and G. We are getting 7 and Bob's public key is 3. By sharing their keys among each other, 7 and 3, we are getting the Li's shared secret key 3 and Bob's secret key the same as 3. So the key exchange was successful and we are getting the shared secret key is equal to 3. So with this, we have concluded our session. Thank you.